Good morning, everyone. So, welcome to another day of HSMA. We are going to be going through decision trees and random forests this morning, and I hope that you will find that these are some really quite pleasantly, I'm sure you'll be quite pleasantly surprised, quite easy code to adapt if you got on okay with the logistic regression stuff last week. And also you will hopefully see some nice, powerful performance on your machine learning problems with these and the techniques we're going to be covering this afternoon. So without any further ado, I'm going to get on. Actually, that's a lie. With some further ado, I've just noticed that there's some messages around the collab exercise links not working. So don't panic if that's also happening to you. I'm going to investigate the problem, but I will also go through an alternative way to get the notebooks into Colab. So don't panic. There will be a way to take part in the exercise regardless. So far, you've got to grips with with a range of the key machine learning and AI concepts over Dan's last 3 sessions. So we've covered how to train a model, how to deal with train and test splits, how to deal with standardization, and how to use sklearn's logistic regression algorithm for predicting classes. So I believe we're working on the stroke data set, predicting whether people should or would not receive thrombolysis. You've also done a little bit on how to assess how well your model is performing, so metrics like accuracy, precision, and recall, and also using ROC curves and the area under the receiver operating curve metric. And last week, we covered the really important aspect of designing and assessing safe and fair models in our ethics section. Now, if you root around in sklearn, you'll realize that these aren't the only models available. In fact, there's a huge wealth of models available in sklearn and actually beyond sklearn as well. In the 2 sessions today, we're going to work through a family of models known as tree-based models. So this morning, we're covering decision trees and random forests. This afternoon, we're covering a range of boosted trees, primarily gradient boosted trees. We'll be covering methods that you may have heard about if you've been reading around the machine learning area called AdaBoost, histogram-based gradient boosting trees, XGBoost, that's the kind of big one you might have heard of, like GBM and CatBoost. No worries if you haven't heard of these, we'll cover them in full detail, but you will hopefully quite like them because they're a great way to get good performance with minimal extra code. So, decision trees. Let's head back to Dan's Desert Island DVDs. You all had a go at this in the first session. And what we could have done instead is create a decision tree rather than the algorithms that you came up with, where you had to assign a weighting and a score yourself to each different measure. We could instead create a decision tree. So we could start at the top, we could look at the movie we have in our hand and say, is this movie from the 80s? Yes or no? If we then go down this branch, let's say it is an 80s movie, we can then ask another question. Is this film a romantic comedy? If it's yes, then it's probably left at home. If it's no, then it's going to go in the desert island suitcase. On the other hand, if we look at the movie not being from the 80s, then we go down and go, well, does it actually contain a robot? If the answer is yes, it's going to go in the desert island suitcase. If it's no, it's left at home. So rather than kind of having these weightings, these different scores that all add up to make this final decision, whether it passes this threshold of is it going to go in the suitcase or not, we follow this nice, simple linear path or non-linear path of should we, which of these branches do we go down? Which of these conditions does it meet? And what should we therefore do with it? But what if this decision tree is a little bit too simplistic to completely capture Dan's taste in films? Maybe we need to actually add another layer of detail. And we can go on and on and on. So maybe the film is a romantic comedy, but maybe if it does still contain a robot, then it's still viable to put it in the desert island suitcase. So we add another layer to our decision tree. We add another layer of complexity. Now, when we talk about decision trees, there are a few main terms to be aware of, nodes and leaves primarily. So we have a root node. This is our node at the very top of our decision tree. We then have a decision node. These are the ones internally. So when you're making a choice, when you're going down a split point. So this is a decision node here, this green one. This is also a decision node. And this is also a decision node down here in our subtree. So we also have within our main tree, we have lots of smaller trees. And at the end, these yellow nodes, we have what we call our leaf nodes, our terminal nodes. This is where we have a final kind of classification of what we should do. So in our stroke, this would be give thrombolysis, not give thrombolysis, for example. So why actually should we bother using decision trees instead of logistic regression? Logistic regression often gives us a really good outcome. Well, for a start, let's imagine one of our features is actually, for example, whether I will like a song solely based on when it's released. And looking at this data, it would seem that I really rank a song highly if it was released in the 70s or 80s. I was not very impressed with the music of the 90s and 2000s, but I think in early 2010, there was a bit of a good revival. So this is best fitted by a sort of U-shaped line, not a straight line, not anything else. It's a U-shaped line. Logistic regression doesn't really do very well with this kind of relationship. It will either incorrectly classify the excellent drum and bass of the early 2010s, or it will do a really rubbish job with the excellent rock of the 70s and 80s. And either way, if I'm trying to train a logistic regression classifier on this, it might struggle a little bit. A decision tree, in fact, instead can cope just fine with this sort of pattern in the data. Our decision tree for this data would say that it would start by looking at whether the song was from 1990s onwards. If it was from before 1970, it's going to say that Sammy will love it. And if it was from before 1970, Sammy won't love it. But if it was after 1970, but before 1990, then I will love it, and so on and so forth. So we can start to capture these more complex relationships. And overall, decision trees are really well placed to capture these nonlinear relationships between features and target variables. So there are ways to make your logistic regression work in these situations. You can create extra features to help capture this nonlinearity, but it will really struggle as it can only create a single linear decision boundary. So if we have a pattern like this in our decision space, we will put a straight line across it and not really have much luck with capturing it. This is a little bit different to, don't disregard the S-shaped curve we talked about last week. That's all still valid. And don't worry too much about the intricacies of what I'm talking about here. I'm just kind of want to give you a flavor of why decision trees may sometimes be a better option. So in contrast, decision trees can build up a really complex boundary. They can really start to capture these complex relationships within the data and start to deal with these huge real-world data sets with lots of features, etc., where there are not simple relationships that exist. The other benefits of decision trees, they're really easy for stakeholders to understand. They're what's called a white box model. This can make it a lot easier to build trust in the model. So we go back to our decision trees, we can show those to our stakeholders and they can understand exactly how things are being built up step by step. They can handle categorical and numeric data. Categorical data doesn't require what we call one-hot encoding. We're going to actually talk a bit more about what exactly one-hot encoding is later. And I am telling a little bit of a lie there because in theory, it does. It doesn't require one-hot encoding. So this is, in short, where we have our categories. We've got, say, for example, whether someone went to hospital 1, hospital 2, hospital 3, or whether our music is a musical music, whether it's rock music, pop music. If we try and stick that straight into our machine learning model, most of them are going to go, oh, I don't really know what to do with this. Instead, we turn them into these columns where actually we have, is this a musical as column 1? Is this a pop song, column 2? Is this a rock song, column 3? And we'll have ones and zeros in that. Go into detail in that later. But in theory, decision trees can deal better with that. As I say, it can deal better with these nonlinear relationships. It can capture the interactions between features. So actually, if one feature in our data set is also kind of linked to another in some way, for example, if we've got, when we have cars that are older, they will also tend to have been driven further. It can start to capture these sorts of interactions, or something else like, if being female has a particular impact on some other feature. You can capture these interactions within logistic regression, but you have to do the hard work yourself. Decision trees are better at just doing that for you. Decision trees also don't require normalization of the data. So remember, we talked about min-max scaling and normalization last week in our logistic regression session. Great thing about decision trees, you don't require that normalization step. Decision trees are also not as strongly affected by outliers as logistic regression, and they're also quite good at handling missing values. Now, missing values can be a real problem in certain kinds of machine learning algorithms. Decision trees generally better at dealing with that. The downsides of decision trees, they are very, very prone to overfitting. They're very prone to learning all of the nuance in your training data set rather than actually learning the generalizable patterns. You might get incredibly good performance on your training data set, try and apply that to a real world problem and find that it absolutely falls over. It has learned every tiny intricacy of the subtleties of your training data set, and that doesn't necessarily reflect the true patterns that are going on in the real world. Tying into this as well, the small changes in the training data can lead to huge changes in what your trees apps actually look like. So if you've got more data and added this into your training data set, then maybe you'd find that it's a bit of it's completely changed what its predictions are. If you then put that tree in front of you, print it out, is going to look completely different, and it's going to be very hard to maybe understand why it's making certain decisions across these different training data sets. It doesn't feel very stable. It doesn't feel very very consistent. So to give you a little bit more about that, so you might have noticed the words variance on the previous slide. In machine learning, we are also always dealing with what we call the bias variance trade-off. High bias means that a model hasn't captured the true relationships in the data very well. It's really just too simple. It's underfitted to the data. It can't, when you then apply it to some new data, it's just going to kind of give you quite simplistic predictions that aren't necessarily going to be very good. High variance means that the model has instead captured lots of noise in the training data, rather the kind of, like I say, those weird subtleties, those weird quirks of that training data, rather than the true relationships that really matter. It's overfitted. If we think back to that sort of line that we might be fitting on a machine learning model, instead of fitting a sort of fairly simplistic straight line that sort of does a pretty good job of splitting the two classes in half, it's instead done an incredibly wiggly line to kind of go, oh, okay, well, we've caught every possible instance of each class, and this is perfect, but maybe that's not a very good way of generalizing to the real world. So a model with high variance will generally do a really good job on the training data, but a poor job on new unseen data. You can't generally optimize for both of these. You've got to balance them. Balancing bias and variance is crucial to creating good machine learning models that have captured patterns while generalizing well to unseen data. In general, decision trees have high variance. They are capturing the noise. They are not generalizing particularly fantastically. A couple of other downsides of decision trees: they can be quite slow to build when data sets are large or have a high number of features. It's not easy to develop what is called a globally optimal tree. Instead, what we do at each decision point, we are making the best possible decision we can to make a good tree with what we have in front of us at the time. So when we talk about an NP hard problem, remember when we were doing our geographic modeling and saying if we wanted to evaluate every possible geographic optimization combination for a larger problem, then it would take all the computing power in the world for maybe 20 years, something like that. Well, that's similar to trees if you wanted to create the most perfectly optimized tree that you can have. So you have to use what's called a heuristic. You have to basically make your best educated guess at that point in time. It will make a good enough tree. Decision tree is also not so great with linear relationships. You can also find yourself creating a biased tree when given an imbalanced data set. So if you've got a data set where, for example, you've got a test that identifies whether people have cancer or not, and actually the vast majority of the people who take this test don't have it, or a very small number do, you've got a very imbalanced data set that you will be training on a very small number of the positive cases, very large number of the negative cases. And feeding this in can give you a very biased tree that doesn't perform all that well on actually identifying those positive cases. So I'm going to pause there just for a second, just to kind of think about all of this. So decision trees don't need to worry too much about the next little bit, how the tree is built. the intricacies of it, but I do think it's useful to know, and some of you will like to understand how the decision trees are made. When we get to the code in a minute, you'll see that actually the code for developing a decision tree is very simple. You don't need to be dealing with all the split points. You don't need to be telling the tree to do much of anything other than optimizing it with some nice simple parameters that we'll go through. But what you need to fundamentally understand is that a decision tree is just another algorithm. It is another way that we can train a machine learning model. It works a bit differently behind the scenes to a logistic regression model, and it is just another tool to have in your toolbox. The other thing about decision trees to understand is that decision trees by themselves often don't perform that well. You might see in some of the later data, in some of the exercises and some of the other examples I'll use, it might not perform better than logistic regression. But what decision trees are a really good building blocks for the models that we will talk about later today, for random forests, for boosted trees. They are the fundamental backbone of those machine learning methods. And so it's useful to understand what a decision tree is, because it will help you to understand how those later models are working. Also, just going to quickly check the chat. Nothing too important, or not important, nothing too urgent in there by the looks of it. Hopefully this is all roughly making sense. The other thing I wanted to mention at the beginning of this as well, and I forgot to, is that machine learning isn't my specialty. I would say that I'm more of a geographic optimizer, geographic modeling and discrete event simulation and web development kind of person. Machine learning is not something I do a huge amount of day to day. I have done machine learning projects and I've used all of the techniques that I'm talking through today. But if any of you are more expert in this area, please do pop in the chat if you notice something that I've either not explained very well, or that you think I've maybe got wrong as well. I really want to make sure that we are not kind of saying anything misleading. I don't want to, leave any stone unturned as well. So do pop in the chat, pop me a direct message, or pop an issue. If you're a GitHub user, you can leave an issue open on the GitHub repository if this is something you've done before. And I'd really appreciate just any feedback on these sessions about how we can make them as clear and as useful and as, as good as possible. So with all that said, let's go back to talking about how trees are built. So let's start out with a set of data that we need to classify. We're going back to my music tastes. And what we've got are only a couple of features in this case, but decision trees can cope with hundreds of features. That's absolutely fine. They do get quite slow if you're trying to work with hundreds and hundreds of features. But for now, just for the sake of this example, we're going to have a song, we're going to have a release year, a genre, and whether I like it or not. So the only thing we're going to be trying to classify on basically is what year was it released and what genre does it fall into. And then we're trying to predict yes or no as whether I like it or not, effectively. So when we then are trying to build our trees up, we need to decide what we're going to split on. So thinking back to the trees that we had for Dan, looking at when was the movie released, did it contain a robot, what genre did it fall into? How do we know which is the best column to use at each point? There are a couple of different ways that we can actually do this. The most popular are, the three most popular are called Gini impurity, I'm not sure I'm pronouncing that right, entropy and information gain. All of these relate in some way to the impurity of a node after making a split. And what do I mean by impurity? Now, let's say that we split on whether the genre is rock. If we go down the yes at this point and look at our data set, we get we find that I've got two songs that I like that are rock and one that I didn't like that is rock. If the genre is not rock, we've got 4 songs that I liked and 4 that I didn't like. Now, this has not created very pure nodes. If we instead split on whether the genre is pop, what we find is we instantly get to a node where all of the songs that were pop in this data set I didn't like. There were 0 likes. We don't necessarily have purity over here. That's unlikely to happen. We'll need to go and do a few more kind of branches to get to a nice pure node at the end over here. But actually, after splitting by genre is pop, we've got a nice pure node over here, compared to splitting on rock, where we've got 2 completely impure nodes. They've got a mixture of likes and not likes left at each step after splitting. Now, Gini impurity, entropy, and information gains are all just a way of kind of putting a number to this kind of comparison. So when we're working out what to split on at each step, we can do the splits, calculate how pure the resulting nodes are, and then choose which are the most pure to be our next, to use that as our split, and then go on to the next split, do that same calculation again for the next kind of column that we want to split on, and so on and so forth. And we just repeat and repeat and repeat until we've built our whole tree. Does it matter which of these you use? You can tell sklearn and in the code which you would like to use. You don't have to do these calculations yourself. It's a parameter you pass into the sklearn decision tree classifier. And when you are building the tree, Gini index is generally quite good for binary classification. So yes or no, or has and doesn't have, those kinds of questions which we've been looking at, like the Titanic survived, didn't survive. It's very computationally efficient in that case. Entropy can be quite good when your data set is imbalanced, and information gain is often a really nice all-rounder, and you'll see lots of examples where people use it, and unfortunately it's not available in decision trees default model parameters, so we won't go too much into it. But all of them fundamentally are doing the same kind of thing. So let's do an example with I've just seen that Dan says it's pronounced Janie, so I'm going to go with that. Let's do an example with the Janie impurity. I don't know if this is trying to if this is true or not, but I'm gonna assume it is, and you're not trying to
I googled it, Sammy. I have no idea, but I'm happy for you to go with that.
Cool, that sounds good. Right, so let's do an example with the Janie impurity. So let's say that we're going with this genre is rock classification. So what we've got are two songs that I like if we do that, and one that I don't like out of that data set that we had. 4 songs that I did like and 4 that I didn't like. Oh, Jeannie seems to be winning in the chat, actually. So anyway, we'll use this formula to calculate the Janie impurity for one leaf. Now, the formula for this is 1 minus the number of positives over the total in the leaf, and we square that. And then we minus the number of negatives over the leaf total, square that. What am I talking about when I say the number of positives in the leaf total? Well, let's work through it step by step. Let's do it on the left leaf first. So the impurity over here is we've got 2 songs that we liked, so that goes on the top. 2 songs that we liked plus 1 that we didn't like, that's the total number of cases in the leaf, so that goes on the bottom. We square that, and then we, on the negative side, the negative case, the not likes, we have 1 on the top, and then we still have the same numbers on the bottom, 2 plus 1, the total number in the leaf, and we square that. And what we get after we do all of this is 0.44444 recurring. What do we do next? We do exactly the same thing on the other leaf. So we have our impurity. This time we've got 4 songs that we liked and 4 that we didn't like, 4 on the top, so that's 4 plus 4 on the bottom, the total in the leaf. On the right, we've got 4 on the top again. Why is that? Because, well, we had 4 not likes as well. 4 plus 4, calculate the Gini impurity here, do all the squaring, etc., and we've got 0.5. Now, how do we use this metric? Well, what we then do is weight each of these by the number of values in the leaf. So on the left-hand side, we've got a total of 3 values in our leaf. On the right-hand side, we've got 8 values in our leaf. It's a total of 11 values. So on the left, our value of 0.444, the value we calculated for this leaf, we're going to weight it by 3 over 11. You know, effectively how many samples that we're looking at in this case are on this side. So 3, which is the number of samples, divided by 11, the total number of samples, times that by 0.444. Do the same on this side. We had 8 values, 11 values in total, times that by the Gini impurity we calculated for this node. And now we are going to have the total Gini impurity. We're going to add the 2 together. So if we do this for our 2 different splits in this case, we find that this one over here, the genre is rock, gives us an impurity of 0.484848. The one on the right gives you 0.469. Now, lower impurity is a better split overall. So we will go, in this case, the genre is pop would be our first split, and we would go from there to do our next split. And like I say, note that we might not always end up with a terminal node after the first split. In this case, we did because we had a nice pure split after the first case, but it may have been when everything was taken into account, either that our data set couldn't come to it, there wasn't a nice simple criterion that it could use to get a perfectly pure split after the first one, or that actually the best split, even if it didn't result in impurity, but the best split overall, the split with the lowest impurity was not actually one that resulted in a perfectly pure node. You can see that these values were actually quite close to each other, even though this one on the outset looks like a better one. But anyway, what might we split on next? We could look at splitting on whether it was released before 1989. That gives us this next decision tree. So this time we've managed to split out to make sure we've got 3 where, again, I like it. So we're starting to build up quite an informative decision tree. We've still got then 5 examples to classify, 3 where I like it, 2 that I don't. We're still trying to get down to some level of purity. So now we can split by whether it's a musical. That gives us 2 that I definitely like, and 3 cases still to classify. And finally, we need to release before 2011.5. And there is a reason for this that I can't remember off the top of my head, unfortunately, that it's not just 2011. I believe this is based on the actual best tree. So Sammy doesn't like it over here. Sammy likes it over here. So we've managed to build a tree to classify that entire data set and get down to a perfectly pure tree. Now, that might not be what we actually want. We'll talk about that in a minute. So as I say, there's some really clever ways to build trees to ensure that it's the best possible tree that it can be, the globally optimal tree. But we do tend to build trees in this locally optimal way. We call it a greedy algorithm. And so it's just making the best possible decision at this point it is at. It's not building out every possible tree and going, oh, okay, actually, this gives us the best tree now. It's making those decisions. It's looking at the data. It's looking at all the possible splits, calculating those Gini index for the possible splits and going, right, that's the best one. So the split on the right might seem like the best choice from what we have in front of us at the moment. But actually, if we went further down the tree, we could have found that a different split might have given us a better tree overall within the constraints we give. But, you know, and if we don't want to sit around for the next 30 years waiting for our tree to calculate, this will give us still a pretty good tree. So I'm going to go through some code example. You'll be pleased to know that's most of the theory out of the way now on decision trees. We're going to return to some code, and the code is lovely. I'm going to apply this to the Titanic dataset from the logistic regression session. So as a reminder, this is a classic Kaggle competition dataset. Do head to Kaggle if you're ever looking for datasets. If you find yourself running out of stuff to do in the exercises, I don't think you will today, but if you do find yourself running out, go and have a look at Kaggle. Go and see what datasets are out there. Kaggle is a great place to find datasets on which to practice your machine learning skills, to try out these different classifiers, to see how to create a dataset a classifier that performs really well on unseen data. The challenge here is to use machine learning to predict which passengers survived the sinking of the Titanic based on the data about the passengers. And then, like I say, in machine learning competitions, people compete with their approaches in terms of accuracy, precision, recall, all the other metrics to determine which machine learning algorithm is best at determining which passengers survived and which did not. Now, what you'll love to know is that the key steps of this machine learning process are extremely similar to logistic regression. We divide our data into features and labels. So our features might be, for the Titanic data set, what cabin were in, what passenger class were they, how old were they male or female? And our label, our output, is just a single kind of column. It's just, did they survive or did they not? That's what we're trying to predict. We then divide the data into our training set and our test set. Now, our training set is what we will train the model on. Our test set is what we keep back to evaluate whether our model performs well on unseen data. Is it just is it doing all this overfitting and doing really well on this very specific training data set, or actually can it move over to the test set and generalize well to unseen real world data, which is what you generally really want it to do if you're going to be putting this model into production. Optionally, we can use k-fold validation here. So actually that effectively our data is being trained on all different, all data gets used as the test once all data gets used as the training. It just gives us a larger data set to work with to evaluate the performance of models on unseen data. But more about that at another time. Now, what we would usually do here with logistic regression is we would apply feature scaling. So all of the data values are all on a similar scale. Logistic regression requires that for it to perform well. In fact, we don't need to apply feature scaling with decision trees. That doesn't need to happen. So that's one step we can get rid of. Now we create a logistic regression model, except we don't, we create a decision tree model. We fit the model on our training data. That's exactly the same as before. We predict Y from X in our training data and in our testing data. And then we assess the performance of the model. We can use a range of things to assess how well the model is doing on this unseen data: accuracy, precision, recall, the F1 score, which we haven't talked about yet, ROC curve, area under the receiving operator curve as a metric, confusion matrices, which we'll also talk about today. Huge amounts of ways you can assess performance, but it's exactly the same as the way you're going to assess the performance in the logistic regression. So how does this actually translate into code? Well, this is going to feel, again, very familiar. Same as last week. I've imported the CSV file of data, and in this case, I made sure that everything is interpreted as a float, as a decimal number. So I've read in my CSV file. These double dots here mean go back one go up one level of folder, then look in the datasets folder. So if we're in our exercises folder, we've gone up to the next level, just the general repository folder for this session. We've gone into datasets and we've looked for the process Titanic data. This won't be exactly the same for all your datasets. Obviously, it depends on where you save stuff, but we'll read in our CSV of data or our Excel file of data, or we'll connect to a database and bring it in that way, but we'll bring in our data. We'll turn everything into a float. So, for example, this is just as a reminder, this is what the data set looks like. This isn't all of the columns, but we have a passenger ID that we're not actually going to want to predict off because that's really not going to tell us anything, or it shouldn't. Whether the passenger survived or not, that's what we're going to be trying to predict. Then what class they were in, how old they were, what their fare was, for example, some imputed ages, etc., if the existing age wasn't there, and so on and so forth. So this data has already been processed to make it ready for machine learning, and we'll come back a bit later to what that means, as most of the data sets you will use today have already been pre-processed as well. But we want to give you the tools to be able to pre-process your own data sets, your raw data sets, so that they will work efficiently and effectively with machine learning models. But for now, we're going to take that data set and we're going to divide it into features. So features are X. It's a capital X because that means there are multiple features, because there's multiple features for each example. It's effectively a 2D matrix. We have rows and we have columns of features. We have labels, which we're denoting with Y. The lowercase is indicating that there's a single output for each example. So all we have is died, survived, died, survived, died, survived. It's a one-dimensional output. So if your data is stored in a pandas data frame called data and our label is stored in a column called outcome, we can store all of our features and labels as followed. We drop the outcome from the existing data frame. So we're saying get rid of the column outcome. How do we know it's the column outcome? That's what this axis equals 1 means here. What we need is just the outcome column. So we take our data and we just say, please just give me the outcome column. That's what these square brackets are doing, is just pulling back a single column of data. We then need to split our data into training and testing sets, and we need to do this for both the features and the labels. We use the sklearn train test split function, which we import from sklearn.model selection. In this case, this line of code will split it into our training and testing data sets. We have training data of our X, our features, testing data of our X, our features. So that's what we'll feed in to try and get our predictions from our trained model. We'll have our training data set for our Y. So that's what we'll be trying to predict from this training data set of X. And we'll have our testing data set of Y. That's what our testing data set is trying to predict. Now, here we can specify how big the test size is. We set 25% of it to be used for testing on, 75% of the data for training. This isn't a perfect, there's not necessarily a one size fits all answer here to how big the test data set should be. 80-20 is quite a common split actually, rather than 75-25, but it depends a little bit on just how much data you have, among other things. This function is returning multiple values. So that's why we are assigning multiple values as the output when we call the function. So we've got xtrain, comma, xtest, ytrain, ytest. That's because this returns 4 separate objects in this order always. So it's important that you do not mix up the order of these, or your data set's going to be all over the place. They're not going to make any sense. Things are going to be trying to learn the wrong things, predict the wrong things, so on and so forth. So always xtrain, xtest, ytrain, ytest. Like I say, in our logistic regression model, we standardized our numeric features. So we were centering, in that case, all our values around a mean of 0 with a standard deviation of 1. Don't need to worry about feature scaling with decision trees or any of the methods we're going to talk about today. But do head back to Dan's slides on feature scaling if you want a reminder of what that is and the different kinds you can do. That's all in session 4B. Now, fitting the model, once we've done our prep work, we've split our features, we've split into features and labels. We've split into training and test data. We've scaled our features. We're ready to fit the model. So actually do the actual logistic regression, except we're not going to do a logistic regression. We're going to do a decision tree. So instead of doing model equals logistic regression and then model.fit, instead we're going to import the decision tree classifier from sklearn.tree. We're going to create a model that is a decision tree classifier. And this line remains exactly the same. Model.fit xtrain, ytrain. We're saying, please fit the model to our training data. Train it on this to predict this. Once it's been fitted, we can then use it to generate predictions. We're testing the accuracy and other metrics in a minute with these predictions. But to generate the predictions, we just use model.predict on our training and on our test data separately. This is unchanged, same as our logistic regression. Like before, again, we can calculate the accuracy metric to give a sense of how our model is performing, but do always remember accuracy can be really misleading. And we can see here that our model is actually returning a much higher accuracy on the training data set. It's nearly perfect on our training data set, and it's not doing very well in our testing data set. And all that suggests is that our model is overfitting. It's matching too well to the training data set. We'll go over some ways to counteract that specifically within decision trees, but as I say, decision trees are prone to doing this. You will often see this pattern of really good performance on your training data and substandard performance on your test data. It's learned not necessarily the patterns, it's learned the nuance of that existing of those data points, not the real patterns. Now, a quick word here on reproducibility. There are elements of randomness creeping into our machine learning code. Remember going back to our discrete event simulations, there were elements of randomness in there. Well, that happens in machine learning as well. So when we do our train test split, if we ran our code multiple times, that we'll find our model metrics are going to vary. Now, this is because the train test split is being done randomly. You're getting a different set of training and testing data each time. You might want to make your model results more predictable and more reproducible for the next person that tries to run this. So we can pass the random state argument to train test split. So all that is one extra argument where we do train test split, x, y, set our test size, and then we say that our random state, in this case, we've used 42, as always. You may also want to do this for some kind of models. Doesn't really matter in decision trees. There's not really any randomness creeping in here, but you can do it. It won't stop you, but for some of the ones we talk about later today, randomness is a crucial part of these models. So setting the random state when you set up your model, when you use this decision tree classifier, that's where you need to set the random state here as well. Right, I've been talking for 40 minutes. I'm just going to give you 5 minutes just to take a quick comfort break, get yourself a cup of tea, and then we're going to talk a bit more about model metrics for assessing and comparing model performance. I'm also going to take that 5 minutes to have a look at the chat so I can come back to you and talk about any of the questions in there. Take a 5-minute comfort break, stretch your legs, and then we will be back at 10:15. Hello, everyone. Right, welcome back, hopefully. I I'll just give it a second, but also for those of you who have been having problems with the collab links, I have hopefully just fixed those and posted the fixed links in the central plaza. Unfortunately, that happened due to trying to avoid the problem with too long file names. In the process, I broke the collab links. So collab links are now hopefully fixed and linked in there. We also seem to have, I noticed a few more people than usual have had problems with VS Code and picking up the environment, even when you had environments picked up before. Not entirely sure why that's happening. There are a couple of suggestions in the chat if that's something that's coming up for you as well. But that is all of that. So to address a couple of the questions that have come up so far, and actually, to be honest, all of them have been answered rather fantastically in the chat. But random state, I realized didn't explain random state very well. I did gloss over that a bit, kind of. So the random state is thinking back to you know, when we were in our discrete event simulations and we were talking about how our models would always, you know, we wanted to be able to simulate different days, different random patterns of people turning up, but we also sometimes wanted to be able to fix the pattern of people turning up so that we could actually ensure that when we change things like the number of beds or the number of nurses, some kind of resource parameter, for example, that actually the changes we were seeing were definitely to do with the change we've made and not with the change in the arrival patterns. Now, when computers are really bad at being truly random. So when we set a random state, like a random seed, they're kind of the same thing in this case. When we set a random state for it to start from, it will then go off and go, oh, okay, my next random number is 3, my next random number is 6, my next random number is 49. If we set a different random seed, it'll go, okay, my next random number is 12, my next random number is 16. But every time we use that same random state, we will get the same pattern of random numbers being generated. And that feeds in then to things like the train test splits, which you know, when it goes through your data frame of examples and picks out examples to use in the training data set and which ones to pick out and put in the test data set, it will make sure that it is picking out those same random samples as long as the random sample parameter, the random state parameter, is kept constant. The other thing is, of course, 42. It's life, the answer to life, the universe, and everything. Hitchhiker's Guide to the Galaxy. Fantastic series of books, and just the universal coding geek standard for your random state. It can be anything. You know, choose a random state that, you know, choose your favorite number. Absolutely fine to use whatever number you want, and there may be instances where you want to change or iterate the random numbers in certain kinds of code. So all it is as long as that random state is a consistent number, it will ensure consistent reproducibility of your results. Just checking that there's nothing else coming up. Oh, I'm seeing Jeannie is actually truly the correct pronunciation, or there's a lot of debate. I'm going back to Jeannie, but I don't think I actually use it again for a while now. So
Sorry
right.
about that, Sammy. I'm going to blame Bing. Bing insists it's Janie. So take away from that what you will about your trust of Bing as a search engine. Google corrected it.
I will lower my estimation of Bing. And yeah, the joy of computers. On that note, for those of you who are, you know, maybe using some of the AI tools to help with coding, for example, don't trust everything it tells you. I'm sure this has already been hammered into you by just the general news, etc. But they can be incredibly helpful. There is nothing wrong with using something like ChatGPT or Perplexity to help you with your code, but it can really send you down the wrong path. Sometimes it can suggest things that don't exist. It can give you entirely incorrect information. I've seen an example of it spending a really long time trying to say that one of the functions with a very specific technique in its name doesn't actually use that technique at all, for example, and only after telling it it's wrong did it finally concede it is wrong. So yeah, Bing, AI, search engines, yeah, we won't go into that today. Anyway, metrics for assessing and comparing model performance. So we covered a little bit of this last week. We want to assess the performance of our model. As we saw, accuracy, or as we've seen in previous examples, accuracy isn't always the best option. So ROC curves are another option, receiver operating curves. Receiver operating characteristic curves. There we go. We took a look at these in the logistic regression session, but as a reminder, they plot the true positive rate against the false positive rate, that should say. The further up the left the diagonal are, your curve, the better the model performance effectively is. So if this was tracing all the way up here, that would be a fantastic model. If it was tracing quite close to this diagonal line, your model's really not doing very well. And if it's underneath the line, then your model's back to front. By looking at the total area under the curve, we can get a nice metric that tells us, is this model better effectively than random chance? And also a nice interpreter way of, does this model perform better than another model? So if I train a logistic regression and I train a decision tree, it gives me a nice way of comparing the performance quite quickly, rather than looking at the two separate curves. But overlaying the curves can be really informative, especially if you're interested in true positives and false positives. Come back to that in a minute. Now, receiver operating characteristic curves can look a little bit strange for decision trees, but they are still useful and a valid tool. So you can see it's a far in this particular data set. This was on the Titanic data set. It's a lot less jagged than the logistic regression one. It's still a good tool, but it is performing less well than logistic regression. So do always try logistic regression. Don't disregard it just because it's not shiny and fancy. It may actually perform extremely well. But there are a range of additional model metrics that we can use to give us a good balanced picture of our model performance. We may prioritize high performance in particular metrics depending on what our model is being used for. Just to recap them, I'm not going to put you through Josh's song, but it's a great song. Sensitivity is a percentage of actual positives correctly predicted. Specificity is the percentage of actual negatives correctly predicted. Precision is something different. It's the percentage of predicted positives that are correctly predicted. And recall gets us back to the start. It's the same as sensitivity. So recall and sensitivity, same words for different words for the same thing. Now, if you come back to this this video, you will never forget those definitions again. I can promise you that. It's a very useful little video, but actually translating that to what that means in terms of your model performance, for example, if you're trying to predict whether a test, is this model good at finding the people that truly have cancer, for example, or not, then, what does that actually mean? What does that translate to? So I'm going to try and move on to the next screen without getting this to play. I'm going to fail miserably. Come on, there we go. Also, just as a side note, StatQuest, I'm sure there's some people in the room here who've used StatQuest. It is a fantastic YouTube channel if you want to dive a bit further into the details of some of these methods. Josh can give more time to them than we can give today, and he is a fantastic explainer, and his book is really good too on the StatQuest Illustrated Guide to Machine Learning. These are brilliant ways to really get a lovely intuitive understanding of how everything is working, whilst also diving into the maths a bit more as well. So do head to StatQuest. I've got some links at the end of today's session as well to videos if you want to enhance your understanding of any of the models that we talk about today. So model metrics. Let's imagine we've built a classifier that predicts whether someone has a disease or not. We've tested the classifier on 100 people and we've compared it with the actual results from the gold standard test. Now, if our model has a low sensitivity, we're going to get lots of false negatives. We're going to get people told that they don't have the disease when they actually do. There's going to be lots of missed opportunities for treatment. If our model has a low specificity, we're going to be getting lots of false positives. We're going to be getting lots of people told they have the disease when they don't. And that can be lots of worry and unnecessary treatment. Now, if we have low precision, a lot of the positive results are actually false positives. So again, we have that same situation, lots of worry and unnecessary treatment. I won't go through this in detail because Dan did a great job of talking about this last week, but just as a reminder, in the slides, there is a bit of a breakdown of all of these different model metrics and what they mean in context. Now, calculating these model metrics, there's a couple of different ways we can do this, and I will talk about various different ways of doing this throughout today's sessions, but one of the ways you can do it is to go to the sklearn.metrics module, import recall score and precision score. Now, precision, we pass in our Y test and our Y predicted test, so we're passing in the true class labels for our testing set and the predicted class labels for our testing set. For now, we're going to use average equals micro. Don't worry about what that means at the moment. I will talk about that later. Recall, again, it's just recall score, same setup. Specificity is the precision score. Sorry, gave myself a moment there. Specificity is a special case of precision. It is for the negative case. So we, instead of passing in the defaults, we say specifically we want pos label equals 0. And now just remember that the closer to 1 you get for any of those metrics, the better. But you might prioritize one over the other depending on what kind of model you are trying to train, what the goal of your model is, and what you need to prioritize. Is it really important that you pick up every single case where someone actually does have the disease and never miss it, even if that means you do get some instances where people are told they have the disease and don't? Or actually, is it better to, is it, you know, on balance, are you willing to have a few that slip through the net because, you know, the alternative is incredibly costly or something similar? It's very difficult to say what is exactly the right threshold to apply there, and it's something that you will have to come to a conclusion for your own specific use case. Now, how can we refine our decision trees? Decision trees can cope automatically with missing values, which is really nice. They have built-in support according to the documentation for missing values when splitter is best and the criteria is Gini, entropy, or one called a log loss that we haven't covered today. Splitter equals best just means it is making the best possible choice at each split point. You can also set this to random, so it will just make a random split at each point. You probably don't want to do that. Choose splitter equals best, and that's what the default for decision tree classifier will be. When training trees as well, we can set a maximum depth for the tree. By default, the decision tree classifier will just keep going until every node is pure, and that's what leads to that horrendous overfitting. You can see that when we've got a tree here where the max depth is set to none, it's ridiculously complicated. If we set the max depth to 5, then instead we get a tree that is far more simple. Now these terminal nodes may not actually be pure, but they may have, you know, let's say 10 cases where it was the positive label and 1 case where it was the negative label. In that case, the majority will be what the prediction is. So it won't be perfectly pure, but it will probably generalize better to unseen data. You'll probably find your performance on the training data set goes down, but your performance on the test data set goes up. So here, for example, we set the maximum depth was no maximum depth. We have an incredibly high training accuracy, but the test accuracy is pretty poor. Set the maximum depth to 7, our training accuracy has dropped, but our test accuracy has jumped up. Now go all the way to max depth of 3, our training accuracy has dropped further, but our test accuracy has also dropped a little bit. Now there's some low element of randomness still into this, but effectively, the further you go with your maximum depth, if you have a very low level of maximum depth, you will have very shallow decision trees. They will be underfitted. However, if you don't set a maximum depth, you will have very high variance. Your trees are very overfitted. So you want probably somewhere in the middle. Try out some different values of maximum depth. And here you can see this just same thing represented graphically over time. If we looked at the accuracy of the training data set, over different maximum depth parameters, higher maximum depth, really good performance on the training data set, but actually we start to see the performance on the testing data set drop up. And it, as I say, it's got this random element. There isn't necessarily a perfect point to set. Now, minimum samples for leaf and split. This is another way of controlling this overfitting. So when the decision tree is deciding whether to split at a given node, we can prevent overfitting by stopping it making the split if there isn't enough data. Now we decide what enough means. We can set the minimum samples for the split or for the resulting leaf. So just as a reminder, we've got our leaf nodes down here. These are our split points, these points where we're sort of going off down a yes or no question, or, down those yes or no questions. So let's say minimum samples for split. This is a parameter that we would pass in when we create our decision tree. And if this point is reached and there are fewer than this many rows of data left, no more splits will take place. So for example, we've got to here, and actually at this point, there is, we've only got 3 samples available. Instead of splitting further, it would now just predict the majority class. We have not met the threshold for the minimum samples for a split to take place. Now, minimum samples leaf. If the split is performed and the resulting leaf nodes would contain fewer than this, many data points, the split just won't take place. So for example, if we tried to split on genre as musical here, it would find that that gives us a nice pure node, but actually it only contains 2 samples, not 3. So it's very, again, we're preventing this overfitting by making it go back a step and either making a split that is less pure but meets the conditions, or just not making the split if there's no split that the conditions can be met for. So if we have a very small number for those minimum samples split or minimum samples leaf, then it will usually mean that the tree will overfit again. If we set a very large number, the tree just can't learn the data. It's expecting too much data at each split point. Again, this will depend a little bit on just how big your data set is as well, and how complex, but you'll need to play around with different values for these to find the best possible tree that you can create. Now, pruning is another way to prevent overfitting and to make decision trees perform better on unseen data. There are 2 ways we can do this: pre-pruning and post-pruning. Now, pre-pruning prevents the tree from growing too complex when we're building it by stopping it before it becomes too complex. Now, in fact, everything we just talked about, the maximum depth, the minimum samples parameters, that's a way of doing it. It's pre-pruning your tree, preventing it becoming too complex when you grow it. Now, post-pruning builds the whole tree and prunes it back afterwards, after the whole tree has been grown. There is a parameter called CCP alpha that you can set when you initialize your decision tree that will be its cost complexity pruning. It's too complicated to go into today. I'm not going to talk about it, but you may be interested in reading up about pruning, particularly post-pruning yourself, if you're going to use some kind of decision tree algorithm in your project. We can also plot the trees. Now, these aren't necessarily the most intuitive. So I'm not going to go into too much detail about them, but I will provide some reference if you want to try and interpret these plots yourself. But it does give you a broad idea of what is going on when under the hood when our trees are being plotted. So there's a couple of examples here in the slides of breaking down some of these nodes, but I'm aware of time, so I'm going to keep going. So the plotting of these trees is actually nice and simple. From sklearn.tree, we import plot tree. We pass in our model. We can tell it our feature names so that actually it knows what these should be when we go through, things like passenger class, fare, cabin number. Otherwise, it will just give us some rather unintuitive numbers. So we pass in our initial data. We get rid of our survived column. We don't want to be passing in the label. We get what columns the names are, the column names, and we turn this into a list and we pass this to the feature names parameter. Class names, we need to pass in what classes there are. So in this case, on the Titanic dataset, it's died, survived. Maybe it's does not have disease, has disease. Maybe it's does not like song, likes song, and so on. But you're just passing this as a list of the classes you have. Finally, we just put filled true, and that just adds in this coloration that makes it a little bit easier to read. Like I say, these still really aren't very easy to understand. There are some other packages that will produce more stakeholder-friendly decision tree plots. There's a nice one called dtreeviz that provides a range of plots. It's a real pain to install. I had a lot of problems with making sure that it was installing correctly, and I didn't want to cause you all nightmares with your environments any more so than I generally do. So it's a bit of a pain. We won't cover it today, but do look it up if you're interested. Have a go at installing it into your environment. That's good practice as well. And it's a nice library for visualizing these decision trees a bit more intuitively and kind of understanding how pure things are at each split. It can also show the path through a tree for a single individual. And it can provide a slightly more simplified breakdown if you don't want all of these additional bar plots, histograms within it. It just kind of shows you the split points that it's making. So what we're going to do now is go away and work through a notebook, the decision tree stroke exercise notebook. Have one person sharing their screen. I would recommend taking another break. Maybe take this at the end of the 45 minutes instead, actually, with the way timing's gone. So I'll work on this, or, you can decide within your groups what works best for you. But we'll work on this for 45 minutes. We'll take a 10-minute break, and then we will regroup at what does that make it? 10:35. I can't do the quick maths. Panic, panic. 10:45. So we'll be back at 11:30, I believe.
Oh, plus the 10-minute break. Yeah, yeah, half 11.
Yeah, so we'll be back at 11:30. So I'll open up the breakout rooms in just a moment, but I'm just going to check any other questions at this point. Everyone hates Bing. Everyone is having arguments with ChatGPT. Someone having an issue with setting up the environment. Failed building wheels for cat boost. I would recommend so you can either remove cat boost from the environment.yaml. It won't be absolutely essential for this afternoon's exercises. So just delete that line from environment.yaml, save it, and try installing again. That will just bypass that package. And that's the same for any of these, particularly the AdaBoost, CatBoost, LightGBM, and XGBoost this afternoon. You don't have to use all of them, or it's a good way of getting around the problem for this morning's exercises, and you can then do that in VS Code, and you can do this afternoon's exercises in the Colab alternative. I'm not quite sure why that's happening in this case. We did have some issues with people on Macs not being able to install LightGBM, but I'm assuming this is different. Emma, if you pop me a DM, I can also take a look if there's anything I can help with there. 42. Amaya asked if there's any situation where we ever might want to use a random splitter. If not, why is it an option? Good question. I'm not actually sure off the top of my head. I would like to know as well, so I will get back to you on that one. Kappa and MCC better at evaluating classification models than F1 and AEC. And Dan has said, yeah, they're very much different aspects of performance. So there's, I think, yeah, for all metrics, I would say look at a suite of metrics. Don't just rely on one. Calculate everything and think about what it's telling you about your model. And that is kind of where I'd go from there. What matters to you for your model that you're trying to create? Sid has asked, does having lots of features in a model result in overfitting? Yep, so it absolutely can. Too many features can add to model complexity. You can also run into problems where your features are strongly correlated with each other. Talk a little bit more later about what that means, but in effect, if two features are kind of telling you the same thing, then that can cause problems as well. The more columns you have, the more rows you tend to need as well to actually learn from it. So you might find that your column, having lots of columns, doesn't tell you all that much, and often you can get very good performance with a very small subset of your columns. That's something we'll cover in the final session of this module. Sorry, I've been not very clear. Are we coding independently with one person showing their screen or coding as a group? I would say I'd leave that up to the groups. It's a notebook that you can work through independently, but I would always recommend having one person share their screen. The cat boost issue, one person had an issue where they fixed it by updating setup tools. So pip install 2 - upgrade setup tools. That's in the chat. Do try that if you're having that issue. And someone is having an issue where Y data profiling doesn't seem to have set up correctly. I'm not quite sure why that hasn't happened because it should have been in the YAML file. I will double check if that's gone missing. You can just bypass that section if it's not working. I will look into why that isn't installing because it should be in there. Right, I think those are all the questions. I will open up the breakout rooms now and I will start moving around and just seeing if there are any issues, but have a go at creating the decision tree classifier, training your models, and go from there. So see you shortly. Hi everyone, welcome back. I hope that felt okay. I managed to get around a couple of the groups, but not all that many. But most of you seem to be getting on okay from what I could see. So a couple of apologies first. there was definitely an error in where I was asking you to get one of the data sets from. That was based on an earlier version of the exercise. I made some changes to make the data import more robust and broke that second data import in the process. Hopefully that provided some useful debugging practice, but I do apologize because it was not meant to be in there. The other one, you may have noticed some slight oddities with the precision and recall scores, the fact that they seem to all come out the same. And that is effectively something to do with the fact that we were using the micro average. We will, as I say, explain later what that means, but it probably was a little bit confusing in the exercise to have them all coming out the same and may have felt like an error. So we'll make a change to that for next year. But hopefully most of you managed to get a good way through that exercise. And I will look into, I've seen a couple of errors come through in the chat as well, so I will have a look into those just in case there's anything I can solve on that one. But for now, we're going to go a little bit further into the next step. So for a start, I'm going to briefly tell you about classification, the difference between classification and regression decision trees. So far, we've only been looking at trees that might predict a class at the end. So that's some sort of label. Is that has disease? Is that will be admitted? But actually, decision trees can predict a numeric value at the end too, instead, which can be really useful sometimes. So for example, you might want to look at something like predicted mean medication costs over a 6-month period. So then you might be looking at still the same kind of features, do people have a certain disease, or are they a certain age, or are they a certain gender? But at the end of each split, what you get to is an average prediction of the costs for these people. We'll do a lot more on this later. We do actually do a regression exercise, but fundamentally, it's just useful to know that you can use trees for these kind of predicting these continuous output values as well, not